Good morning. Welcome. Welcome to Denver on behalf of the North American Catalysis Society. We meet here today for the 25th time, as our forefathers first met in Philadelphia in 1969. It was their wisdom at the time that brought us here, as we hope the wisdom of today will bring us back for many generations to come. We need to share our science and to come closer as a thriving community of practice. There's a record number of participants, as you will find out from the numbers that you will hear later today. But even more impressively, there's a record number of our young here. I have to admit that walking through the reception last night felt more like a college campus than it did a meeting of philosophers at the mountaintop. So I felt out of place and yet also at home. We meet this time as the guests of the Rocky Mountain Catalysis Society, with their beautiful Rocky Mountains as a backdrop. We thank them for their hospitality, for all the hard work that went into this, and as you will see, for a job very well done. The success of the meeting, however, from this point forward, depends a great deal on all of us, on our willingness to share our science, to have open discussions. So it is in your hands, and therefore my message is to go forth and succeed. The meeting is now open. The podium belongs now from this point forward to both the organizers and to those of you whose science we came to hear. With that in mind, I invite to come to the podium Brian Richards, who's one of the co-chairs of this meeting.
Telling the first thing is Atlantic City.
Good morning. I'm Brian Richards from the Colorado School of Mines and the Rocky Mountain Catalysis Society. On behalf of the entire organizing committee, welcome to NAM 25 in Denver, the Mile High City. Hopefully most of you had a chance to check out the Pinnacle Club last night. It was a spectacular sunset. I'm still amazed we were able to get 900 people up there in 25 minutes for that opening reception. As a matter of housekeeping, we will need to reset this room for the oral sessions, so we kindly ask that following the plenary lecture that everybody exit to the coffee break so the crew can get that going and we can keep everything on time. It's my real honor to introduce the Uschi Houdry Award. Uschi Houdry was a real pioneer in the field of catalysis. Spent a career working in the area of environmental catalysis and was really one of the leaders in terms of development of the catalytic converter. I'm going to keep this very, very brief. I'm going to hand the floor over to Hayam Abrevea, who is a colleague of this year's award winner. Thank you.
Good morning. I have the honor and pleasure to introduce Dr. Jeff Brinker, the winner of the 2017 Eugene J. Houdry Award in applied catalysis. Jeff's innovations in alkane dehydrogenation and thiol oxidation, as well as his leadership in the field of catalysis for industrial refining and petrochemicals, have led to commercially proven superior catalysts, more energy efficient processes, enabling conserved world natural resources and improved environmental stewardship. Jeff received his PhD in inorganic chemistry in 1983 from Ohio State, directly after which he joined UOP. He then rapidly moved through the ranks from research specialist to research director. For the past 10 years, Jeff has been leading the UOP research organization that responds to changing fuel demands, feedstock supply diversification, environmental challenges,
and cyclical shifts in supply and demand, delivering breakthrough technologies in all areas of refining and petrochemicals, including novel catalysts for propane dehydrogenation, methanol to olefins, toluene tense alkylation, reforming, ethylbenzene conversion, green jet, ionic liquids for alkylation, and several new materials for gas separation and adsorption. Outside his regular job duties at UOP, Jeff serves on the advisory board of the Dalian National Lab for Clean Energy and the Molecular to Mesoscale DOE-funded Energy Frontier Research Center in Stony Brook. In addition, Jeff helps organize UOP's refining panel technology discussions held every other year with major refining and petrochemical companies. Jeff's innovations and 61 US patents have been recognized with multiple awards, including the ACS National Award for Creative Invention, the UOP Stein Star Award given for the best breakthrough of the year within UOP, and the Honeywell Distinguished Technologist Award given for outstanding technical contributions over the course of a career. In addition to the patent literature, Jeff has contributed papers to the open literature, including his recent descriptions of catalytic dehydrogenation and thiol oxidation in topics in Catalysis. Jeff is scientifically curious, open-minded, a good listener, and humble. He has a great sense of humor and loves basketball to the extent that he thinks he could have been a basketball coach had he not pursued science. Without further ado, I would now like to welcome Dr. Jeff Brinker to the podium to deliver his award lecture. Jeff.
Well, thank you, Heidi, for that very kind introduction. And I did coach basketball with my daughter's 5th grade basketball team. It was a lot of fun. I'm really honored to be here. I want to thank the non-organizing committee and the Houdry committee, and also Clariant for sponsoring this award. And it's really a special honor for me to be here and have a chance to speak with all of you, because this is really a special gathering of the leaders in the world of catalysis and materials, and sharing ideas. And it's my favorite meeting every other year, and I'm very happy to be here. So much, I think we have 17 people from UOP at last count, but every day another one comes, so that's a good thing. Including, I think we have at least 6 scientists that are in an early career. And we've hired some outstanding people from many of the professors here, and I think you're doing an excellent job of training students, top-notch students, and I hope they enjoy this conference. And with that, I'll start my presentation. Just a brief outline. I'll say just one slide on UOP so you know where we are. Then I'll talk about selective oxidation of thiols. Then I'll get into dehydrogenation. First, ethylbenzene with oxidative reheat. Then paraffin dehydrogenation for both light paraffins and detergents, including some oxidative reheat work we've done there. And then I'll summarize. My basic message, I'm not going to read this slide, but we're going to have our 103rd anniversary this summer at UOP. That's 103 years. I'm a little shocked I've been there for 1/3 of the company's history and it still survived. But it's been an excellent company to work for. We're doing the same things we've always done. Develop technology, working on 75 projects every year, catalytic adsorption processes. We've expanded a little bit into, quite a bit into natural gas, and we have renewable technology now that's out in the field. So, but it's the same basic company, and we love what we do, and that I'll move on to the content. So selective oxidation of thiols, it was my first project at UOP. It's done with an organometallic cobalt thiocyanine that's derivatized on the rings as shown there. It's a reaction to convert thiols to disulfide selectively in fuels. It's very largely employed around the world on all feedstocks, from heavy feedstocks like kerosene all the way down to LPG and natural gas cleanup in different process forms. It can be used in extraction or fixed bed catalytic reactions under mild conditions, liquid phase, dissolved oxygen, and alkaline solution. This catalyst is very special because this thiocyanine ligand is a very strong field ligand. If you remember back to those days when we called such ligands that, like cyanide. So it stabilizes, and that's important for two reasons. In this process, H2S will carry over, hydrogen sulfide will carry over, and it will pluck the metal out of almost anything. If you try to use a porphyrin here, it's going to pull the metal out as metal sulfide, and the catalyst will be deactivated. But not for the thiocyanine ring. You can feed 8% range H2S to this, and it won't demethylate. The other reason it's important is it can stabilize different oxidation states of cobalt that you normally wouldn't see, like cobalt 1 D8 low spin. So think of it like cyanide almost in terms of its potency as a ligand. What's the reaction chemistry? In a little more detail, you're doing a 4-electron reduction of oxygen to water. But of course, over this kind of catalyst, there's no way you can do that in one step. It goes through hydrogen peroxide as an intermediate. So two electron transfers, and I'll show you what we think the mechanism is. And our goal was to eliminate caustic because many refiners are concerned about caustic because it carries over cresol, cresolates, and so on, and then that becomes a hazardous waste to dispose of later. So our goal was to remove the caustic from the process. And I'm summarizing a lot here because I can't go through everything, but what I found was that there's 3 functions of caustic. It accelerates, it's very important to accelerate hydrogen peroxide conversion to water. That's very important because you cannot build up hydrogen peroxide in FCC gasoline, right? With diolefins and benzylic hydrogens and so on. It'll degrade the fuel very quickly. So that intermediate you will not see, or at least we never saw it when we do catalytic reactions in this system. The other thing it does, which is non-obvious, is it removes deactivating gums from the surface. All fuels have a tail end on it. You make some heavies, and that's very important. And it's non-obvious because we feed very low levels of caustic to this process. The third is obvious. You deprotonate the mercaptan, you make a mercaptide, and I'll show you how that works in a little bit. It's very good at attacking the cobalt. And this reaction is unbelievably selective in the presence of, say, FCC gasoline, olefins, benzylic hydrogens, and so on. It's almost 100% selective. Uh-oh. Sorry. That's the end of the talk. So the basic mechanism is, I studied this a lot by ESR and UV-Vis and different techniques, is you have the cobalt-2 chelate. The mercaptide will come in, much like we learned about heme chemistry, where nitrogen from imidazole or another nitrogen peptide comes in and bonds to the DZ squared orbital in the axial position. That activates it for oxygen activation on the other side of the ring. And we can see that by ESR. You can follow it. You can see the cobalt-2 with all the hyperfine splitting and everything of the nitrogens. When you bond the mercaptide, it disappears. It goes ESR silent. I mean, I claim it's cobalt-1 low spin D8. Within UOP, there's some people think it's a closely coupled ligand radical anion, where the radical is on the ligand. And it doesn't really matter to us in industry, but someone here can figure it out, I'm sure. But what happens next is, after the oxygen binding, there's a very fast reaction to generate disulfide, release hydrogen peroxide, which can re-enter the oxidation for a second mole of conversion. And the important aspects are, it's really a concerted electron transfer, so the catalyst itself has to have a really balanced redox potential. It's very selective because the oxygen activation, this cobalt thiocyanine isn't very good at oxidation until that mercaptide ion bonds to it. And that really activates And that's why it gets an unusually high selectivity. A little bit more, you know, when I started on this project, it was interesting because it looked like we had a non-caustic catalyst that was active but deactivating. But we found out something very different. When you take the caustic out, it really changes completely. The reaction mechanism is completely different. It goes to a free radical mechanism. But that's not so easy to detect in real fuels, because when you look at the top two experiments, we were still able to convert all the mercaptide. But when I started looking, but it was deactivating, as you can see in experiment 2. But when I started looking at where the mercaptan was going, it wasn't going to disulfide, and that was the first clue that it was a different chemistry. So I started doing experiments like with thiophenol is the predominant mercaptan in FCC gasoline. And so it's very reactive. It can go by an anionic or thiol free radical reaction. So if you look at it actually without any caustic present, you can convert it completely, but it deactivates quickly, and it makes a polymer of thiophenol, which deactivates the catalyst. So I started thinking, well, experiment 5, octane thiol, it's going to be much less reactive to a radical reaction than the aromatic thiol. And in fact, we had no conversion with the octane. Oh, I'm sorry, that's a typo. I'm sorry, there's no activity whatsoever. Oh no, with caustic there's 100% activity, experiment 5, of course, because that's an easy mercaptan to convert. Experiment 6, you take the base out, there's no conversion, no activity whatsoever, because you can't initiate the radical reaction with a normal thiol, not effectively. And so then we did additional experiments where we put oxidation inhibitors in, and that even shuts down but just simply, this just shows an overall picture. You want to avoid combustion, steam reforming over the platinum catalyst we use, or dealkylation and combust to hydrogen, as I show. So we've developed a modified platinum catalyst that was stable to agglomeration, you eliminate all acidity, stable support, and eliminate diffusion limitations. And I'll show you just how severe the diffusion limitations are in a minute. It actually even surprised our reaction engineering group at the time, because you're talking about hydrogen reacting with oxygen, right? So how large do the pores have to be to eliminate diffusion limitation? Well, that's just a function of how fast the kinetic rate is, right, relative to the diffusion rate. And so when I started this project, it was a fair amount of pressure, to be honest, because they had started testing large-size catalysts, and the catalyst lasted about 60 hours, and the target was 2 years. So I got called into the meeting, and they said, hey, we want you to work on this because we need to deliver catalyst to the Mitsubishi demo unit in 9 months. So that's a little bit of pressure when you're new in a company. But we had a good team. We were able to get a first-generation catalyst out that lasted as long as we needed for the demo unit, 4,000 hours. And then we were able to improve the catalyst over the last 2 or 3 years. So I'll tell you a little bit about that. Just to show you how this works in real life, maybe I should point over here some of the time, the distance from the inlet of the catalyst in millimeters. So this is a very thin bed. And it has to be with a large size catalyst, because you cannot increase pressure drop. If you increase pressure drop, you undo any advantage you would have by burning hydrogen. And there's a couple things I want to say. If at this point you've used up the oxygen, there's no oxygen at the outlet of the catalyst, this extra catalyst here, because it's an adiabatic reactor, I should say. So you've combusted all the hydrogen, the temperature's flat, there's no heat loss. And if you analyze the back end of this catalyst, it's very interesting. There is no pore structure left of the original catalyst. It's completely coked. But you do see pore structure, and in fact you see the pore structure of the carbon deposited in the alumina pores. And you can prove that by burning it out and so on. So that's interesting, because even in the top of the bed, only the exterior of the catalyst is really active. So you have to, the effectiveness factor might be on the order of 0.05, something like that is the way to think about it. And so this just shows some commercial data. Very selective. Our target was, 88% selectivity. We were plenty selective, and activities remained high through the run. Now I'll show you some factors how we got to that improved stability. And that started with changing the alumina type and the pore structure. It's showing 3 aluminas here, and in the final state of being a high-ordered alumina, like think of alpha and theta, that kind of alumina. And really the key is, if you look here at the relative stability, alumina A has 67% of its pore volume, and pores larger than 1500 angstrom. And it's a very low density material if you look at the piece density there and high pore volume. So it needs to be a very open structure. That's one criteria. And the effect on stability is much greater than the effect on initial activity. For the reason I said, any platinum, for example, located inside the pellet, you've lost it to coke. The other thing, if you take alumina C and look at the particle size effect at the bottom, at this is a diameter 3.5, 1.3.6, you'll see the relative rate constant, first order rate constant, increases significantly for smaller particles, but the big effect again is on stability. It's very remarkable. Stability is very highly affected by the amount of effective platinum that can be reached with the proper pore structure. And so through this, it's how most of the improvement was made. And the end result of that is we've been able to offer that with alumnus. You can get a big capacity increase, even up to 70%, but in full smart you can go to very high conversion and get a large capacity increase by simply adding oxidation catalyst into the dehydro reactors. I move on now. Next technology I want to talk about were the light olefins. And I'm going to particularly talk about propane to propylene by on-purpose dehydro. And what I want to really say is, probably you know this, but propane dehydro and both MTO have taken off. They're becoming a very high percentage of the light olefins made in the world. And that's because of the feedstock advantage of coal in China being cheap. And in the rest of the world, I'll show you the propane-propylene differential. And also driven by the propylene gap because of available ethane. I think you all know this, the naphtha crackers are all switched over to ethane, and you don't make propylene in an ethane cracker. So that increases the demand for on-purpose dehydro. And I'll go through a little bit of marketing just to show you context. So what this slide basically says is that the propylene gap is going to be filled by on-purpose dehydro at a 17% growth rate. That's huge in this industry because the base market's very large. And that, I'll show you more data in a minute. And the other, from steam crackers or FCC production, the rates are much slower. And why is that? Why would that be? Well, there's a strong economic driver, and that is the propane-propylene price spread, which is really quite remarkable. So you may not be able to read it in the back, but let me just pick a number. In 2015, if you go up, the difference in value between propane and propylene is something on the order of $700 a ton. So if you build a 1 million ton plant, that's $700 million of uplift in value. You can spend a little bit of capital for that. So it's very attractive. And if you look at this plot at the IRR versus differential, so if you take that 700 delta point, the IRR for a now small 650 kMTA unit is close to 40%, 35–40%. Of course, the units now are 1 million tons, so that's even more attractive. So there's a next strong economic driver to do this. We were fortunate, we started on this technology a long time ago in the 80s, well, actually in the late 70s, early 80s. And it's difficult technology to do because it's equilibrium limited, so it requires high temperature, low pressure, like ethylbenzene, highly endothermic. So reheating strategy is important. And as propane conversion formation is unavoidable in our hands, short catalyst life's required. We're okay with that at GOP because we have this machine called the CCR. So we don't mind 3 days life. We like it. So you don't have to design the catalyst for life. Again, you can kind of cheat. You worry about activity, selectivity, don't worry about stability because we can return the catalyst to its fresh state or equal to the fresh state. And you really can't separate because of the complexity of this, you can't really separate the catalyst and process. So just to give you an idea of equilibrium, when you're talking, we can do C3 through We can do butane now, of course. We've always done isobutane, and we can do C5, iso-C5 particularly. But you can see the temperature required for a reasonable conversion of propane. You know, I'm sorry, I'm sure I can go back. You're talking very high temperatures for a catalytic system, continuous process to achieve good conversion. And it has the same enthalpy situation almost exactly as ethyl benzene, except you don't have so much steam diluent carrying heat in this case, so it quenches quite quickly. So you take the paraffin through, you go through the endotherm, your conversion stops, you have to reheat, we use interheaters, and so on. And that's the way the thermodynamics are dealt with. You know, I want to recognize so many people contributed in this area. I can't recognize everybody at UOP, but the original dehydrogenation team, if you talk about dehydro at UOP, Vipin Vora, who led development, and our petrochemical leader, Tom Oimai, they're involved in all this. They're very important to the original ideas, to the development, to the inventions. Additionally, this young guy here, who we hired in 1985 from Ohio State, I might have had a little bit to do with that, because he was in my group, and when Tomo asked me, who's the best student you know? Like, do you know any great, I said, I know one. I was supposed to train him in Dr. Shore's group, and when I went down to training, he ended up training me as a new student, because he was running 7 reactions at a time on a vacuum line, working up 5 products, all simultaneously in his first month in a group. So he's done outstanding at UOP. He just was, he got the Pines Award from the Chicago section. And last but not least, sitting here is Haim. Haim was very important in the area of PAPOL and also advanced Oleflex, which I'll talk about. And we worked as a team. Actually, we had a lot of fun. 4 of us here formed like a task force for PACOL dehydro. We met every day like in the war room. Our SEM couldn't tell us the platinum distribution at the low level of platinum we used, so Haim would cut the pills in half, reduce the platinum, and we would go in with a magnifying glass and decide which catalyst to test. Because you literally could see the platinum with your eye, but you couldn't measure it even on the Macron microscope at the Archaeology Center at Chicago at those days, because it's very low platinum. So that's the team. The Oleflex process, which I worked on the regeneration of the catalyst with DY, which has to be modified for this process, works in the following way. You have multiple reactors. Let me go one more slide. You have multiple reactors depending on propane or butane feed, and you have interheaters. So you go through the reactors and you reheat between stages. I won't talk about the downstream. It's very conventional. It has positive pressure. It has small reactors, and you can change out catalyst on the fly. You don't actually have to shut down. You actually don't have to shut down. You can load fresh catalyst because it kind of goes through like a plug flow. So when you get to the end of the catalyst life, you can just put fresh catalyst in and take used catalyst out. And that's big because no one likes to take shutdowns. The reactor design, and I had nothing to do with this, but I like to show it because our engineering is just marvelous to me, because this is the reactor side of the CCR, where it's the reactor inlet is again a radial flow, this time in to out, and catalyst here is flowing from a lock hopper and it's reduced and then flows down screens continuously. So in that process diagram I showed you, that catalyst travels at least 1/4 of a mile, and it's a sphere, and you don't want it to break. And so that's a big target, right? Round spheres that don't break on this long journey under these tough conditions as they form coke and so on. So this is an important part of the design because of low pressure drop and mechanics. So I worked primarily on the dehydro catalyst design with, at the time, DYGen. And we're on our 7th, going on our 8th generation now. It's, we need long life. Customers love that. Reproducible performance, high selectivity. Actually, our catalyst, nobody ever believes this, but I'll say it again, it's 100% selective. All the byproducts in this process come from thermal cracking. We can back out the thermal cracking and show it's 100% selective, right, within our ability to measure. So that part's good. We can do it selectively by, I'll talk about that later. and then resistance to regenerator and lower metal. And so the catalyst design, of course, the support is very important, how you modify the platinum cluster. And so this just shows you a photo of those spheres, which you may not be able to see, but they're pretty perfectly round and nearly perfect and strong. That's not easy to do. They have to have chemicals. They have the chemical stability you need because you're taking it from reducing condition at 650 C to a carbon burn oxidation condition across the regenerator. And in order to make the catalyst selective, you need to eliminate acidity, diffusion limitation, and maintain surface area so that you have a small platinum cluster that has the right modifier. And so the key part of this is the support, one key I should say, the key. And so you need sufficient surface area to disperse and redisperse the platinum after carbon oxidation. Through our regenerator, I can say it's as good as fresh catalyst. We don't lose any performance against. We can bring the catalyst back to its initial performance. Actually, sometimes better than we can manufacture it. So after a few cycles, the catalyst is actually better than coming out of the manufacturing plant. We try to minimize that, but that's what happens. And I did a lot of work, again, coming from the smart world, styrene world, to eliminate diffusional limitations while maintaining enough surface area to get the platinum function. And that was important. Physical stability, I talked about these. There are many supports you can think about, except I wouldn't recommend silica for this one myself. Alumina, mag oxide, other oxides, and there's work by us and others on interesting supports and mixed oxides. And we prefer alumina type for this because we can control the modifier levels on that support. The reaction chemistry, when you eliminate all side reactions of acidity and other things, really you're only worried about consecutive reaction to diene and coke, which happens. We have this aberration-corrected stem. It's been a great tool for us, great tool for catalyst scientists because you think the active site is X. This is what I made. It's got this many atoms in it, this many modifiers. And then when you see what it is, it gives you a lot of ideas because the closer you look, the more you find out it's not what you think it is by these techniques. So they have great value to catalyst scientists. And we have a great microscopy group. Chem is here at the meeting, Steve Bradley, Sergio Sanchez. They do a great job. And I'll show you a little more on this. We also do XAFs and XAS, of course, because you can average that way. And the only point of this slide is showing that for hexagonal clusters, of course, versus spherical clusters, if you look at the number of atoms and nearest neighbors, we can determine something from that information for a platinum cluster. We published a paper and gave some talks. Simon Bear, who's here, Shelley, I mentioned Steve Bradley, Wharton is a big player in this. Our belief that the clusters aren't spherical when they're small. They're rafts. We know this. Now, it may not be that, I don't know if that holds up in all systems with all supports, but with our support it's true. And in fact, now with the advances we've seen in the aberration corrected stem, we can see all the atoms. So the purple's there for your eyes, but the black circles are actually individual platinum atoms in a 21 atom cluster. And so now we can look at all the cluster sizes. Up in the left, I show how many atoms are in a distribution of cluster sizes versus a number of clusters. So that's pretty good information if you're a catalyst scientist. So you can see there's a lot of clusters with about 8 atoms in them, very small, and they're rafts. They have enough energy between the alumina surface and platinum that they lie flat on the surface, and that's very important because, of course, we're not using platinum, we're using modified platinum. And so you can start thinking about where do I put the modifiers and so on. So I acknowledge the great work by our group down there, Shelley, Wharton, Sergio, Steve, and Archie. This is very important. And I started mentioning this, I'll go quickly, but it's not an academic, for us, it's not an academic matter. With each generation, we've lowered the investment of platinum significantly from the original catalyst. And that's like refinancing your house too, because the platinum cost here can drive a reload. So in other words, if you reduce the platinum enough, there's high incentive for the producer, the Oleflex producer, to actually change out the catalyst, just based on that. And as I mentioned, we can go back and forth in the oxidation and reduction and get to the original state for years, for hundreds and hundreds of cycles. That was a lot of work. I want to recognize Adrian Sockler sitting here. He figured a lot of fundamentals out about this regenerator for Oleflex, which has some complications compared to like a platforming regenerator. And Adrian did a great job of figuring out the fundamentals of the regenerator so that we can accomplish this. Modifiers, you know, all the great work is by you here in the audience. I don't think we published anything, or very little, but there's some fantastic work on how group 4 modifiers and other modifiers interact with platinum. So we love reading your papers, and outstanding work. I think we agree with the conclusions that it's an electronic effect primarily. I read Alex's recent paper on that theoretical paper. We believe that. What we had seen in our own work is weaker platinum diolefin bonding, less coke and less CC carbon breaking. That was our observation. We really didn't know if it was an electronic effect, but I think that's certainly a big player, and again, some fantastic work out there by these groups discerning that. What about Oleflex commercially? It's a big area. We've licensed over 40 units in the last 5 years, and they're getting bigger and bigger. Now they're about 750 to 1 million tons. So there's a lot of propylene capacity, and I showed you the reason why it occurs. And so it's a very active area for us around the world. They're everywhere. China, the US, some of the big units are in the US, coming to Europe soon and other areas. Russia, there's one put in Siberia. Sieber, great company, great Russian company, built that thing in the middle of Siberia, started up, ran perfectly. Not easy when it's minus 40 out. And that's an example of how we do it. We can do ISO C4, and people do still want that in other parts of the world, and mixed units are not a problem. Well, particularly in this case, DY, Chaim and I worked on, of course we couldn't leave it alone. You know, we had to tinker, and so we contemplated using oxidative reheat here, and actually did a lot of work on this. I went through this slide so many times, I won't go through it again. So why don't we apply the smart idea to LP, you know, to light paraffin dehydro? Again, we're cheating. We don't have to have a vanadium catalyst or an oxide catalyst that can do a concerted reaction, which is extremely difficult to do. I mean, that's like the holy grail, right, of catalytic, one of them in catalytic research, with high conversion selectivity. We can cheat. We can burn the hydrogen like we did in SMART and then do the dehydro. The problem is, because the catalyst life is short, you have to have a dehydrogenation catalyst that can also be your oxidation catalyst and be selective for both. Now, I asked our engineering group back in the day, and the famous Tony Vickers at UOP, and of course I knew his answer would be sure. It's like falling off a log. Moving 2 concentric beds through radio reactors with screens, extremely difficult. So our goal was to come up with a single catalyst that we could do this with, and actually we did that. We've got a catalyst that it's 95% selective for burning hydrogen, and it's just as selective as our Oleflex catalyst. So we could do this if we wanted to. If this were the next best technology for Oleflex, we can do it. Now I promise you I'd talk about equilibrium a little bit. You see, this is, the top curve here is, let me do it over here. So if you did oxidative reheating isothermally, and you combust 52% to be isothermal, and I could have called this oxidative dehydrogenation. So this would assume a perfect oxidative dehydro with some isothermal temperature profile. So it's a calculation. That's the conversion advantage you can get over Oleflex. Here's the advantage you get by cheating. If you do 4-stage adiabatic, like I only showed 3 stages, where you're just combusting hydrogen interstage and taking the endotherm so the temperature profile is not optimum, you're still doing pretty well. If you can do this commercially, you're happy. You don't have to do that to be successful. So when I said earlier, oxidative reheat is almost as effective as oxydehydro, from our point of view commercially, that's the case. Not theoretically, but practically, you can do pretty well. Here's an example, in fact, where we did oxidative reheat, and at very high space velocity, at much lower temperature than Oleflex. This is the overall conversion of selectivity including the combustion of hydrogen. So you can see that the selectivity is actually much higher than Oleflex because you don't have any thermal cracking in the inner heaters. So you'll get a net benefit of higher yield per pass and high conversion. We're just changing conditions during this run. I can't really show you that part. And so we have many things going on for the next generation Oleflex. There's a strong team now, research and development. We have another generation of catalysts, better heaters, and so on. And we can do C4, and we're working on the next generation process. Last topic I'll talk about is LAB. And at least I'm old enough to remember as a kid walking down the beach and having foam in the sand. So originally when alkyl benzene detergents were developed, they were made from propylene tetramers, so they had this kind of structure, and the bugs can't biodegrade them because of the branches on the chain. So this is the Rhine River in 1958. That's foam from detergent. And I could show you 20 pictures like this in the United States of foam on the beach. And so UOP took advantage of this before my time in the late 60s to develop a process to make LAB. And that uses kerosene-derived normal paraffins. And that now is over 50% of the market. And well, actually, because you have natural detergents that are linear. As far as catalytic processes, almost 100% of the market. By the bugs can't route. And I won't go through this in great detail other than to show you that we take kerosene from refiners and we treat it with the Molex to remove the normal paraffins, and we return that kerosene with them normal paraffin free. And they like that. That's a good product for them for jet fuel and so on, right? For all the reasons you know. And then we take that into dehydrogenation, and then we're 50%